we said yesterday that if we are dealing with two financial institutions, let's say Bank 1 and Bank 2, okay, and I've got a savings account or some kind of account that is going to provide me compound interest. Okay, now this is a little bit different. What I hope you guys understand is that these formulas that I talked about yesterday, these are not the only formulas that govern finance, right? Okay, there's a lot of other things, a lot of other ways that certain funds kind of mature and generate dividends and all that kind of stuff. This is just one of them, and this is kind of the simplest way, is that we just put in an amount and we are then hands off. We don't do anything with it after that. Does that make sense? There are types of accounts called annuities in which you start with a principal, maybe very similar to the principles that we start here, but then every month you add something to it, or every year you add something to it. Does that make sense? Like an IRA or a 401k or something like that, retirement plans. Those are different formulas. Okay? We'll talk about what an annuities formula looks like, because it's very simple for us to kind of work through once we talk about series and sequences. Okay? Which you guys talked about. You guys remember talking about arithmetic and geometric sequences? An annuity is a geometric sequence. Okay? So we'll do that kind of stuff not next week, but the following week. Okay? So if I'm working with just simple compound interest, and I'm going to deposit, let's say, $500, and I'm trying to decide what bank to go with. Okay? Let's say Bank 1, they can only go compound. Let's go monthly. Bank 2 can compound continuously, right? Okay, now I still don't have enough information to see which one is best, okay? Because I'm going to have an interest rate information as well. So let's say my interest rate here is 3%. Let's say the interest rate over here is 3%. And it doesn't really matter the time. As long as you keep the time the same, let's go 5 years. Because now, there's a lot of variables here, right? Principal is a variable, rate is a variable, compound is a variable, time is a variable, right? All my variables except for compounds are the same, right? So we talked yesterday, if that happens, what is always the best choice? Continuous. Because the more compounds, the more times your money regenerates as an original principal, right? So your dividends are going to start earning you more money sooner in the compound continuously than it does monthly. Even if I just said monthly compared to maybe Bank 2 finds a way to get me an extra compound, so they do it 13 times. 13 would be better than 12, right? Okay. Now, so banks maybe they can't compete in regards to doing that. Maybe this bank cannot change from monthly to continuous, but they can do this. Now you have two variables that are different, right? So now that you have two variables that are different, you have to do the algebra. You have to do the evaluation. Plug the principal in, plug all your N's and R's and T's in, and evaluate and see which one yields a larger return. And then that will allow you to make that decision. Okay? Some of these questions, guys, they will not, so they'll keep it this way. They'll keep everything the same except for the compound, but then they'll eliminate the principal and it won't tell you what you're putting in. Okay? Does it matter what I put in? No, as long as it's what? The same in both banks. Okay? I don't want to put $100 in and then in Bank 2 put $1 billion. That doesn't make any sense. Okay? So I think the easiest thing to do, put one bucket. Okay? Because I'll be able to find the pennies then that I generate from this process, correct? Okay? And compare those, and whichever one gave me more, obviously, is a better result. But I would get the same result as my decimal place would just be in a different spot than somebody that put 10 in, or somebody that put 100 in, or somebody that put 1,004 in. Okay? As long as those are the same, you're good to go, right? Sometimes they don't give you that, and sometimes they don't give you that. They'll just say, bank 1 offers compounding monthly at 3%. Bank 2 says compound continuously at maybe 2.8%. Okay, and they say which one's best. The two things you're missing are principal and time, right? As long as we choose them to be the same, principal is the same as principal and time to be the same time, you should still be able to make a valid argument. Okay. What's a good thing to let principal be? 1. What's a good thing to let time be? 1. Okay. And then you can make that decision. So those are just some things to think about as you continue to work on that 4.2 assignment. All right, so like I said yesterday, this stuff's not going to go away. We're not going to talk too much about interest, compound interest today. Because we're going to introduce logarithms, and the reason we're going to introduce logarithms is so that in a couple days, maybe tomorrow or the next day, we can then go back to those formulas and say, okay, now we know the amount that we want after a particular time. I want $10,000. Well, right now I only have $7,000 available to invest. I know my interest rate, and I know they're going to compound it continuously. How long do I have to wait before that $7,000 matures to $10,000 and I can pull it out and make the purchase I want? Does that make sense? The way I solve them for that t, because that t at time would have been in the exponent, the way I do that is I use the inverse or the inverse function to get that exponential variable, that exponent variable out. Okay. The inverse of the exponential is the logarithm. Okay. So that's what we have to do as introduce logarithms before we can start doing those types of equations. Eventually, guys, our goal, algebra 3 is an investigation of equations, right? An investigation of functions. So if you think about it, our goal is to solve equations that incorporate variables in the exponent and incorporate logarithms in the original equation, okay, or the word log. In order to do that, we have to understand how exponentials and logarithms work together, okay, or how one is created from the other. Every exponential function, a to the x, with a being greater than 0 and a not being 1. So that's the definition right there, that first line definition of what we said exponential functions look like, right? Okay. Now we're going to have a vertical stretch out front of k if we want to, but just the simplest is a to the x. Okay. It is 1 to 1. Okay. Now it's been a while since we talked about 1 to 1, but a 1 to 1 function. Remember, to be a function, it meant every x value has one and only one y value, right? Every x value has one and only one y value. That's a way of saying that we pass the vertical line test. Okay. If that function is what we say 1 to 1, then it also passes the horizontal line test, which is a way of us checking or testing to see if every single y value has one and only one x value. Okay? If every single y value has one and only one x value, then when we reflect that over the line y equals x, we get a curve that is also a function of past the vertical line test. Okay? So this happens. This thing here is 1 to 1 because obviously it passed all those horizontal lines. But when I unplugged my smartboard. All right, so I draw the line y equals x in here. Okay, when I reflect that blue curve then over that line, it's going to look something like that green curve, right? Now the idea is that when you reflect over that y equals x line, we want that reflection to be a function. Is that reflection a function? Yeah. Okay. But only graphs that are 1 to 1, only graphs that pass the horizontal line test, or functions that pass the horizontal line test, are going to have inverses that are functions. Okay. So we talked about that previously with like parabolas. A parabola is a function, right? But if I reflect it over the line y equals x, it looks something like that. Does that red curve pass the vertical line test? No, so that red curve is not a function. Okay? It's still a parabola, but it's not a function. Okay? So every exponential is going to have this property. It's going to be 1-to-1. So it's going to have an inverse. Okay? If you remember the notation we used back with inverses was this thing here. So the inverse function f with that superscript of -1 is called the logarithmic function with base a, and it's denoted by log base a. Okay? We use the base is always that subscript. Okay? So that allows us to define what a logarithm is. Okay? So let a be a positive number with a not being 1. So here's the thing. If logarithms and exponentials are inverses, okay, remember when we defined a exponential, we said a could not be 1, right? Same thing here then. Okay? Your base cannot be 1. And I'll show you kind of the thing that happens if a is 1. So the logarithmic function with base a then, which is denoted log subscript a, is defined by this. Okay? Now here's what I want you guys to understand, because this is where you're going to, at some point, we're getting closer and closer to you guys being in higher level math courses in which you're going to be some independent learning, right? So you might have to read a theorem or read a definition like this one and see these symbols and see what do those symbols mean. Does anybody remember what that means there? Okay, kind of. This double arrow represents this. It's equivalent to that phrase right there. Do you remember what that means? IFF? IFF, or that double arrow means this. If and only if. Does anybody know what that means, though? Because that phrase means a particular way that we interpret log base a of x equals y if and only if a to the y equals x, and how we apply it. What if and only if means to us, guys, is it says if log base a of x equals y, then a to the y equals x. That's what part of if and only if means. But the complete interpretation of if and only if does this. If a to the y equals x, then log base a of x equals y. Those two phrases, and you can see all we did was we flip-flopped the if and then parts, right? Because remember back to geometry, those are, each if and then statement is called a conditional, and when you flip the if and then, it's called a, remember? Start with C again. No. Remember converse? Okay. And if we have a conditional statement and its converse are both true, you write it as a biconditional, which is this. Okay. But what it means to us as a biconditional is that both this red statement and this blue statement are true. So it doesn't matter which side you start with. If you start with an exponential, you can then rewrite it as a logarithm. If you start with a logarithm, you can rewrite it as an exponential. Kind of meaning what Fanny said is that they undo each other, right? A logarithm undoes an exponential, but an exponential undoes a logarithm. Okay? When you see a phrase like this, okay, that's very important for us down the road because it implies a particular procedure on how we interpret and apply and utilize that information. Okay? So these two things are both true, and they're both encapsulated in that phrase. And my hopes are you see, well, this is kind of lengthy to write out up here, right? This is not lengthy. Okay? I think there's more information up top. Okay? It's more obvious what we're trying to get at. But mathematicians aren't really worried about whether it's obvious or not. They're worried about whether they can say the most with the least. Okay? So this says the most, but it's very, very simplistic in its appearance, right? Okay? It says the log base a of x is the exponent for which the base a must be raised to give x. Okay? That is, think about this. That is what, when we ask what is a logarithm, the answer to that is always, it's an exponent. Well, think about this. If I use this approach here, okay, I start with a logarithm, a of x equals y. A raised to an exponent comes back and gives me that x. Okay? So I'm asking what exponent, come over here, it's the y, right? What exponent do I raise my base to so that it gives me x? Okay? So that answer of y, or what y is, it's an exponent. Is that okay with everybody? Some terminology. Obviously, A is called the base. A lot of times, and they'll kind of jump in and out. Let's put parentheses around that part right there. Anybody know from last year what that's called? We also talked about it in geometry when I had like sine of whatever in those parentheses or cosine or whatever in those parentheses. Remember what we referred to those things as? Those are referred to as the argument. Okay? So you might hear me say, what's the argument of this logarithm? It's that value, the value that I'm getting when I raise my base to an exponent. Okay? So to kind of show you, kind of created a GeoGebra the other day that helps kind of maybe use this property or understand this property. It allows us to type in the base and the argument there. We've got our definition on the right-hand side. Log base A of x equals my exponent, if and only if A to my exponent is equal to x, right? Okay? So you see that when we ask the question, what is a logarithm? A logarithm is the exponent that I raise my base to. So I take my base and raise it to that exponent that spits back the argument. Okay? So here you see, okay, if I start with 3, log base 3 of 9 equals 2. To transfer that into an exponential format, I'm asking, okay, 3 raised to what power? 3 raised to the second power should come back and give me 9, right? You guys remember this idea? Like if I start here, this is, I always visualize this. I don't necessarily always draw it, but I visualize it. Start with that base. There's your exponent. Comes back and gives you your argument. So I start with my base, so I write that down, 3. I come across, I know that that's my exponent, 2. It's going to come back and give me my 9, and that's exactly what that's doing for me, right? Okay. You can, because it's an if and only if statement, you can reverse it, which means you can kind of start with that, which means basically I'd be doing this. I'm starting now with this side here. I've got my A, which that's my base. Okay, so that is always your base when you go to the logarithm rule. So I'm going to write logarithm. My base is 3. Okay, well this is my exponent. Well, my exponent, when I write it in logarithmic form, is all by itself. And that needs to come back to 9, right? Does that make sense? Okay, now I always, because I struggle, I don't know if it's because of the way when I was first taught that we always start with the logarithm and transferred it into the exponential. But I struggle going from the exponential to the logarithm. So when I'm done, I just undo what I did. Okay, so I got log base 3 of 9 equals 2. I just check this 3 raised to the second, come back and give me 9, and it does. So I know I've got it written correctly. Okay, so just doing that I think is a good thing to understand. So what this means then, if I take log base, let's go base 10 to get an argument of 1. Hopefully that makes sense. And let's look at it this way. If I say 10 to the what power will come back and give me 1, well 10 raised to what will give me 1? 0. Anything raised to 0 will give me 1, right? Okay? So here's the concept. Doesn't matter what my base is. Let's go, and maybe I can do, I think I've got a slider here for my base. 10. Show object, there we go. Just to make it a little bit easier here to see, My base can be anything, right? That makes sense? As I'm doing that, whatever my base is, does that 1 ever change? If that 1 never changes, does that 0 ever change? No, so the log base of anything, and you're going to see this here in a little bit. The log base of anything of 1 is always equal to 0. Okay? That's the only way I can come back and give myself 1, right? Okay? Now, let's think about this. Why can A not be 1? Log base 1 of 1 equals 0, right? Would you agree with that? It doesn't. Log base 1 of 1 also equal 1? Don't we have a contradiction there? Okay, we have two things that evaluate the same number. That's a problem. Okay? So that's why we don't let our base be 1. Okay? Which is nice because then going back to exponentials, we didn't let the base in the exponential be 1 either because it was 1 raised to anything is just going to give me 1 back. Okay? So try to keep that in mind as we go on. All right, so what, now my base can be anything, my argument can be anything. Let's say my argument is 2 and my base is 10. Let's think about how this works. Okay? It is saying that when I think about taking 10 and raising it to the first power, we think about usually our exponents as integers, right? That's what we've liked so far. Positive or negative numbers or 0, or positive whole numbers, negative whole numbers or 0. But now I need to raise, think about 10 to the first would give me 10. I want to get back 2, right? So doesn't it make sense that I need to use a number that is between 0 and 1 to do that? So you're seeing that if I raise it to the 0.301, 10 to that is going to kick back a 2. So it's giving me kind of that fractional, that rational exponent to kick back that 2. We're going to let our calculators allow us to evaluate, find those values for us, but there are approximation techniques that we go through to evaluate this number by hand, but that's not necessary. Base can be anything. Okay, so if I want to take 3.14, I want to take 5, okay, and get 2 back from it, I have to raise it to the 0.6. Okay. I take pi and I want to raise it to something to get 12 back. Okay, I got to raise it to 2.17. That kind of makes sense what's going on there, guys? Okay. I'll post that under section 4.3 if you want to use that little calculator to help you maybe understand this concept a little bit better. The rest of this PowerPoint kind of just targets examples, not the entire rest of it, but the good portion of it just references examples. Okay, so they're talking about going from logarithmic form here to exponential form. So I have log base 2 of 1/8 equals -3, going down to that third one. The reason I want to show that one is because it's a little bit different than what we've seen. We see here that our argument now is a fraction. If I take 2 to the -3rd, does that give me 1/8? Well, 2 to the -3rd is rewritten that way, right? And 2 to the 3rd is what? 8. So we do see that 2 raised to the -1/3 does come back and give us 1/8. Okay? So it's allowing us to find that exponent that we have to raise a base to provide some desired value. Okay? And again, the goal of learning all these definitions of logarithms and exponents and the properties that are then results of the definition is so when we get into equations, okay, or those story problems where I'm trying to solve for a time or something like that, we can do those things efficiently. Okay? So I want to show you 4 properties here. We kind of just already showed you 4 properties of logarithms that I don't want you to memorize because I think memorization is going to mess you up. You're going to get things confused. But I want you to understand these relationships based off of the definition, okay? And you can easily check these and easily come up with these if you understand that initial logarithm rule. Logarithm base a of x equals y if and only if a to the y equals x, right? These are true based off of that definition. So these are little proofs. I'm going to write them out as like phrases or anything like that, like a complete proof, but this would be the algebra that we walk through. Think about this. Is this true? Why is this true? Well, if I apply the definition, I was going to say take a, raise it to the 0. What's that always going to come back and give you? 1. Because that's true, that has to be true. Okay? And that's what I showed you here when I let my base be anything, but my argument again was 1. So that was this thing here. Where'd my b go? Let's do this way. You see that when I move that b, okay, the base is changing, but that never changes away from 0, right? Okay. So that's true. What about this one? Okay. Well, a raised to the first power, does that always come back and give you a? So what that means to us, obviously a is anything it wants to be. Log base, let's say 3 of 3 is always equal to, well, think about this. 3 raised to the what is going to come back and give me 3. 3 raised to the first, right? Has to be. The only way that I can get something to be itself is to raise it to the first power. Okay? Or anything to be itself through the use of exponents is to raise it to the first power. That is a special case of number 3. So you see how that was 1, right? A to the first gives me a to the first. Well, then a to the x, isn't that always going to give me a to the x? So this is just, number 2 is just a special case of number 3 when x was 1. Okay? But if I take my rule here, say a raised to that power is going to come back and give me that thing. That's true. So this must be true. And if you think about a specific example of that, get one erase that. Think about a specific example. It would be like log base 2 of 2 to the third. Well, what do I have to raise? That's my argument, 2 to the third. Well, I have to raise 2 to get that. That should be 3, right? Okay, it's kind of a form-fitting thing. You know, I take my 2, that's my base. We'll have to raise that 2 so that I get 2/3. So what has to go here so that I can get this 2/3? Obviously has to be a 3, right? Okay, so that 3 is what we're putting there. The last one, a little bit trickier, I think, because again, it's going from this format, a to the x equals y, if and only if log base a of x equals y. I got that back. A to the y equals x. There you go. All right, so we're starting with this statement there, matching that one. Does that make sense? Okay. So do you see, I think highlighting here is useful. Do you see how that A is that A? Okay, so I'm going to write that. So if those are, so that A, when I change it to a logarithm, becomes the base, right? So I'm going to write log of A. So that A right there is that A, which is the same as that one, which is that one. Okay? Now, this part here is the y up there. Does that make sense to everybody? So then when I go over here, doesn't that go to the other side of the equation? Okay, so that log base A of x is over here on the right-hand side. And now this here is matching to that there, which then when I apply the definition, it becomes the argument. So it goes right there. Did I just generate, through the use of the definition, going from an exponential to a logarithm, Did I generate a true statement? Log base A of x equals log base A of x. Yeah, so that's true. So what we see then, and these are kind of recognition things, like I said, if you memorize them, that's fine. My hope is you understand the relationship and based off that definition. If I ever see this, so if I see 2 raised to the 2 log base 3 of 5, I don't want to put 2 there. 2 raised to log base, I messed everything up. 2 of 5, I don't know why I put that other number in there. 2 raised to the log base 2 of 5, because that base of the exponential and this base of the logarithm are the same. What's my result going to be? It's going to be 5. Okay? You can check that. Your TIA 384, guys, I think with logarithms, especially if you got the older version, they're not very useful because they use just a common base of 10. Okay? Some of the newer versions allow you to adjust the base. But I like GeoGebra because I can type in the word log, and now see what it does? See how when I type in these commands, it will tell me the things that I need to allow it to write the correct information. So B stands for the base. I need to type the base in first, followed by a comma, and then my x, which would be my argument. Does that make sense? So if I want like log base 2 of 5, that evaluates it. I'd like to see it written this way. You see how there, if I write log base 2 of x, it puts the 2 as the base, the x is my argument. So now the question is, if I take 2, raise it to the log base 2 of 5, see what I get back. We get 5, right? Okay. So that's kind of how you maybe would use GeoGebra to evaluate logarithms. If I just type in log of x, okay, it's going to, I guess the GeoGebra is defined. I just type in log of x to use the natural log, which is fine. Yeah. If I go log base 10 of x, that's, you guys remember that being called the common log? Okay. Let me write this real quick. If I go log base e, we'll talk about this more tomorrow, log base e of x, are those two graphs different? No. So ln of x is just a different way of saying log base e of x. Okay. All right, so the last thing I want to talk about is how we graph these things. Okay. You guys remember that because these things are inverses, okay, inverses are reflections across what line? I graph them. Y equals x. Okay. If you remember the process for finding what an inverse looks like, okay, that's going to be the kind of the original technique we use to graph logarithms. So I'm going to say I want to graph y equals, let's just go log base 2 of x. Okay. When we graph logarithms, our argument is going to be the variable. Okay, it's going to be the x that we're looking for. Maybe it's 2x or 3x or whatever. Might be another expression. Might be a quadratic or something like that. Okay. But right now, just an x. The way that we deal with this in regards to finding the inverse is that we're going to apply the definition of a logarithm, which says, take my base, I'm going to raise it to the y, and then that'll equal x, right? Remember talking about taking, when I have a square root, don't I square things? When I have a cube root, don't I cube things? Or vice versa, start with the next square, do I square root it? I use the inverse to start solving, right? Same thing here, okay? Now, if you remember back to those things when we used inverses, the last step that we did is we interchanged the x's and the y's. I interchange the x's and the y's, now I get that, right? Do we know how to graph 2x to the y? Oh, sorry, I'm going to say another thing. Do we know how to graph y equals 2 to the x? We know how to graph that, right? Think about this. We know that on that graph, we're always going to have 0, comma, k times 1. 0, comma, k times 1. Well, our k right now is just 1, right? Okay? So I'm going to have the point 0, 1. Okay? We're also going to have the point 1, comma, k times a, right? Well, k is 1, a is 2, so I have 1 comma 2. Okay, so 1 comma 2. I also have then the point -1 comma what? 1/2. Going back to the kind of the general form, it would be -1 comma k times 1 over a. Okay, or you just want to call it k over a. Those 3 points are on that exponential. So by knowing that the exponential and the logarithm are inverse of one another, therefore their reflections across the line y equals x. Remember, if you have a reflection across the line y equals x, if a comma b is on f of x, then then what is on f inverse of x? You guys remember?
1/2.
Okay, so if that, then BA is on f inverse of x, right? So all you gotta do is flip the order of terms, correct? So I think you guys are tell me what you have 1/2 -1. So 1/2 -1. You'll have 1 comma 0, and you'll have 2 comma 1. So those 3 red points will be the key points that we use to graph our logarithm. And now an exponential, our 2 to the x had an asymptote that was the x-axis, right? Log base 2 of x is going to have an exponential. I don't know why I keep saying words that don't matter or don't make sense. Log base 2 of x is going to have a asymptote of the y-axis. Does that make sense? Okay. Because if I take the x-axis and reflect it across the line y equals x, it becomes the y-axis. Take my asymptote, reflect it across y equals x, it becomes the vertical asymptote. That is your y-axis. Okay. Meaning then, an exponential function obviously is not going to be it has, a domain of all real numbers, right? An exponential function has a domain of all real numbers. Does a logarithmic function have a domain of all real numbers? Is there an ordered pair over here that's negative for x value from a red? No, I can't get over that. That's an asymptote, vertical one. I can't jump over here. So I cannot take the logarithm of a negative number. That's why when you go, I come up here and I say log of -3, undefined. Okay? The domain does not exist of it. So when I graph these 2 things, just kind of showing you the comparison here. We had 2 to the x. Then I have log base 2 of x. Okay? If I plot the point, like we said, we had 0 comma 1. If I plot 1 comma 0, it shows up there. I had 1 comma 2, so I should have 2 comma 1. We had -1 comma 1/2. Not 12. 1/2. And then we should also have, then on the other curve, 1/2 comma -1. All right, so taking those critical points off of our exponential, flipping them, then gives us critical points on our logarithm, right? Okay. Now, if you want to use that route, that's fine. There's another way of doing it. We could do this. We could say this point here, f is always, so it was correlating to this point here. This point here was always -1 comma 1 over a, right? So won't this be 1 over a comma -1? Okay. This one here will always be 1 comma 0. And this one here will always be a comma 1. Okay. And if you want to put that k with these, that scalar multiplier out front, you can. But those might, if you want to learn formulas for your key points off your parent functions, where A is your base of your logarithm, okay? You can do that through that process. Have a wonderful day. Stuff getter.